There's a fundamental difficulty with numerical integration of Hamiltonian systems, and that is that numerical methods in general induce artificial excitation and or damping in nominally Hamiltonian systems. So let's start with a simple example. This is a one-dimensional simple harmonic oscillator. The Hamiltonian for this system is equal to 1/2 p squared, where p is a canonical momenta, plus q squared, where q is our one-dimensional generalized coordinate. We know from past experience that this system is equivalent to writing z double dot is equal to negative omega squared z for some real valued omega, and the solution for the system is given by z is equal to some constant c times the exponential of omega naught times time. If you work out the Hamiltonian version of the solution, what you will find is that we can write a state qp at a time t plus delta t, which is equal to, that is, the propagation of the state composed of our coordinate and momenta at t plus delta t is equal to the linear system given by cosine sine negative sine cosine times that same state qp at time t. And you will recognize that this is a rotation matrix in 2 dimensions. So the Hamiltonian version of the simple harmonic oscillator literally looks like a pure rotation in the phase space of the generalized coordinate and its conjugate momenta. I strongly encourage all of you to take a few minutes and ensure that you can recreate this solution. Remember that the forward Euler method is a direct first-order linearization, equivalently a first-order Taylor expansion of our dynamics. And so by inspection, we can write the linearization of this linear system, and that looks as follows. We are linearizing here about delta t equal to 0, and remember the small angle approximations give us cosine going to 1 and sine going to its argument. And so this matrix becomes 1 delta t negative delta t 1. This is a strictly Hamiltonian system, and so our Hamiltonian is equal to the energy, and that means that the total energy, to within some constant factor, can be written as p squared plus q squared, and must be constant. For this first order approximation, if we write out p squared plus q squared at t plus delta t, we'll find that it will equal 1 plus delta t squared times the original p squared plus q squared at t. And so we instantly see that the forward Euler method, which this is a representation of, is not conserving the energy. Rather, it is modifying it by a factor of 1 plus your time steps squared. If your time step is very, very small, then this modification will be very, very small. If your time step is large, then this modification will be large. We can compare this to the effects of a fourth order Runge-Kutta, and in that case, find that it is modifying the energy by a factor of 1 minus 1/72 times delta t to the 6th plus in decreasing orders of delta t. The basic finding here is that numerically integrated systems are not Hamiltonian. They are not energy conserving, and they are not conserving of the fundamental constants that make the system Hamiltonian. In order for us to get at an integration scheme that preserves the Hamiltonian nature of our systems, we need to back up and think about what it really means for a system to be Hamiltonian. And here we are aided by what is known as Liouville's theorem. Liouville's theorem states, for a Hamiltonian system with generalized coordinates q sub I and conjugate momenta p sub I, we can define a phase space distribution function rho such that rho, evaluated at all of the coordinates and all of the momenta, determines the probability that the system will be found in the infinitesimal phase space volume dnq dnp. Again, a lot to unpack in this one statement, so before we move on to the actual theorem, let's just make sure that we're on the same page with the basic definitions. We define an n by n dimensional phase space composed of all of our generalized coordinates and all of our conjugate momenta. It is easiest to visualize this for just the scalar case, like in this case, the simple harmonic oscillator, where we can just plot coordinate versus momentum. But in general, this is an nth dimensional space where you're plotting all of the coordinates against all of the momentum. So in the simplified case where you just have one coordinate and one momentum, Q and P, you will have trajectories within this space. And they can look like kind of anything, but let's, for example, consider something that has an orbit in this space. So remember, this is not a physical orbit. This is something that has a conserved value of Q and P together, much like the previous example where we had Q squared plus P squared is equal to a constant. So this is our phase-space trajectory. And for any point in time, we can define an infinitesimal volume. In this case, it's an area because this is just 2D, but in general, this is an nth dimensional plot, and so it becomes a volume. And this is a dq dp volume. The probability that our trajectory is going to live inside of this volume at some point in time is given by this density function or phase-space distribution function, rho. The result here is the Liouville equation. The time evolution of this density function, d rho dt, is equal to the partial of rho in time plus the summation over the n coordinates of the partial in rho with respect to qi times qi dot plus the partial in rho with respect to p sub I times p sub I dot. And what Liouville's theorem is telling us is that this total derivative is 0. The distribution function is constant along any trajectory in phase space for a Hamiltonian system. This is the most fundamental definition of what it means for a system to be Hamiltonian. The area of any small patch of phase space is preserved as time progresses. So if you take the bundle of trajectories within this small chunk, and you think about all the possible trajectories of the system, and you trace them forward, if the system is Hamiltonian, then for any point in time in the future, when I draw that box, it will bundle the same density of trajectories. Not necessarily the same ones, but the same density. So this is a kind of a very fluid mechanics way of viewing these dynamical systems. It's thinking about densities of system points within some local neighborhood of a given point traveling through the phase space. And that density is going to be constant in time, specifically for Hamiltonian systems. Because we think of rho as an analog to density, we can take that metaphor further, and we can explicitly write rho is equal to the limit as delta v goes to 0 of n of delta v divided by delta v, where delta v is that phase space volume, and n is the expected number of system particles within delta v. And another way of saying that is n is equal to the integral over the phase space volume of the density function rho in the phase space volume, dnq dnp. And these dnq dnp should be understood as dq1, dp1, dq2, dp2, all the way to dqn, dpn. The evolution of rho is governed by what is known as the continuity equation. And this looks very similar to Liouville's equation, but is not quite the same thing. What this is telling us is that the element rho qi dot, and rho pi dot, which are the arguments of these partials inside the summation, is what's known as a conserved current. So we compare the continuity equation with Liouville's equation, and we can write as both of these equations are giving us statements that equal 0, we can mix and match however we wish. we pull out a q dot I times the partial in rho in qi plus a pi dot times a partial in rho in pi, which goes to 0. And the remaining terms are rho times dqi dot d partial qi plus d pi dot partial in pi, which via the Hamilton's equations, we can reformulate as rho times the second partial in h in qi pi minus the second partial in h in pi qi, which we can flip the order of these. And so this is giving us 0. What this is telling us is that the total number of systems entering a volume in phase space must equal the total increase of systems in that volume. Hamilton's equations tell us that P dot, Q dot, the velocity field has a 0 divergence. These are all equivalent statements, and these are all getting to the heart of what it means to be a Hamiltonian system. Hamiltonian systems are volume preserving in phase space.